Artificial intelligence does not magically know answers. Every response produced by a modern AI system happens through a process called inference. This is the stage where a trained model applies what it has learned to new input. Before inference begins, an AI model must first be trained. During training, massive datasets of text, images, or audio are processed so the model can learn patterns hidden inside the data. Training adjusts millions or even billions of parameters inside the neural network. These parameters encode what the model has learned about language, images, or other signals. Once training is complete, the model stops learning. Instead, it begins performing inference, applying its learned knowledge to new questions or inputs. Imagine typing a request into an AI assistant. The moment you press enter, a pipeline begins that will transform your question into a response. Your input first enters a preprocessing stage. Here the data is prepared so the model can understand it. Text is broken into tokens, images are resized, and signals are normalized so the neural network receives structured input. Each token is converted into a numerical vector that represents meaning in a high-dimensional mathematical space. These vectors allow the model to perform computations on language. The encoded input now enters the trained neural network. The network contains many layers of interconnected nodes designed to transform information step by step. Each layer applies mathematical operations using parameters learned during training. These transformations gradually reshape the input representation into something the model can interpret. At the smallest level of the network, an artificial neuron calculates a weighted combination of its inputs and passes the result through an activation function. Millions or even billions of these tiny computations occur simultaneously as the signal travels through the layers of the model. As information flows deeper into the network, the representations become more abstract. The model gradually extracts higher-level patterns from the input data. Eventually, the transformed signal reaches the final output layer of the model, where the system prepares to generate a prediction. For language models, the output layer calculates probabilities for many possible next words or tokens. Mathematical selection strategies then determine which token is most likely, allowing the model to continue generating text one step at a time. The chosen output leaves the neural network and enters a post-processing stage that converts raw predictions into usable results. During post-processing, tokens may be combined into words and sentences, formatted into readable text, or transformed into labels or predictions. Within moments, the AI system produces a response that appears on the user's screen, completing the interaction that started with a simple question. This entire sequence, from receiving input to generating output, is what engineers refer to as AI inference. Inference powers a vast number of AI systems used in everyday life, from chatbots and recommendation engines to translation systems and search assistants. In healthcare, AI models perform inference when analyzing medical images such as X-rays or CT scans to detect abnormalities. Autonomous vehicles rely on inference continuously to identify pedestrians, traffic signals, and other vehicles on the road. Customer service platforms also rely heavily on inference, allowing AI assistants to generate responses to user questions in real time. In many applications, inference must happen extremely quickly. Even small delays can affect the user experience or system safety. Low latency becomes especially critical when AI systems interact with humans or control physical devices, such as vehicles or robots. Large-scale AI inference often runs inside massive cloud data centers containing thousands of powerful servers. Some AI applications perform inference directly on local devices such as smartphones or cameras using edge computing. Inside these infrastructures, servers handle thousands of inference requests simultaneously from users around the world. Specialized hardware accelerators such as GPUs and TPUs allow these computations to run efficiently at enormous scale. Engineers often optimize models for faster inference using techniques like pruning, quantization, and model compression. From phones and vehicles to massive global data centers, AI inference quietly powers the intelligent systems that increasingly shape the modern world.